record on this computer.
Recording in progress.
And today class day 52, right?
52.
Yeah.
52.
Yes. So class day 52, and we are doing a study uh, module 7, the equipment installations. Equipment installation. So equipment to equipment spacing, equipment installation height, about all those things we are discussing. So what we discussed so far, I think we have discussed about the layout drawing preparation so far. Now, when we are doing the equipment installations, for that, let us take this 3D view again. So when we are doing the equipment installations, an equipment installation we are doing on the support structure, and plus in order to do the main bus bar stringing, we are using the support structure. So we are using the tower and gantry in order to support the this conductors, the flexible conductor through which we are making the bus bar, our main bus bar, our transfer bus bar, a common bus bar. So we are making the common bus bar, and that stringing we are doing with help of the tower and gantry. At the same time, when we are doing the equipment installations, we are installing on the support structure. So this support structure are this tower and gantry that uh, design to be done by the structural design engineer in case we are doing any utility project except the power grid, because in the power grid VGCIL they provide their standard drawing for the all equipment support structure and for the towers and for the gantry. But if we do any industrial project, or we are doing any renewable based project, maybe solar or wind power plant, in that case this calculation for the tower and gantry, these calculations need to be performed, and this to be performed by the civil engineer, by the civil structural engineer. But before performing this calculation, the civil structural engineer will ask you some input. So you have to provide that input. So like for that, like they need to consider what is my conductor weight coming on this, what is my conductor span coming on this, what should be the height of this gantry above the ground, or maybe about this beam at this tower type, what type of tower we are proposing, with peak without peak. So this with peak without peak we are proposing, but civil will need this as an input, and then they will perform the calculations, and for their calculations they will take several other factors. For example, they will take what is the zone of this site where we are installing, and what is the wind speed, and based on the wind speed they will calculate the wind force which is coming on this structure, and what is the like electrical short circuit force coming on the structure. So this electrical short circuit force, wind speed they will take from the standard, because every country have their country zone wise, they have standard wind speed. Like for example, in India we follow the IS 802. So in IS 802 the zone wide wind speed is given. So taking that wind speed they will calculate the wind force. Civil engineer will do automatically. But in case of this structural design, they will ask that and along with this wind force, they will also need to know what is my conductor weight coming on this, what is my static tension, what is my dynamic tension, or we can say how much force coming on this structure, this support structure like gantry and then tower. So when they are asking about the force, so we need to provide all the conductor details. They are static tension, and plus we need to provide the tension or force coming at the event when the fault occurred in this substation, or when any short circuit occur in the substation. So what happened at the event of the short circuit? We are taking the one video and an example to understand about the short circuit. So this is test on rigid conductor by FGH Mannheim. This is agency that we are doing. So tube they are using, and the size of the tube is outer diameter is 120 millimeter, and then wall thickness 5 millimeter. Distance between conductors between might be R2Y Y2B 1 meter. Distance between supports 11.5 meter. Initial symmetrical short circuit current 39 kiloampere and peak short circuit current 103 kiloampere, and duration of short circuit 300 millisecond. So when they are taking this system parameters, and when done taking that how much short circuit force coming on the conductor, so they have recorded one video. Let us see this video available on the YouTube as well. So if you want, you can check through the YouTube as well. So you can see over here, like there is a like attraction and repulsion forces between the conductors, and there is swing between the conductor, right? This is the tubular bus bar. Then this much swing you can see, and like you can see here, due to that this damage. In case this is the flexible conductor, then this swing would be very much high. This is in the case of tubular bus bar, but in case of the flexible bus bar, the swing would be so much high. So what we need to calculate? We need to calculate that at the event of the short circuit, how much force coming on this equipment and equipment support structure, and how much swing coming on that, how much the like deflection coming between the phases. So all this we need to calculate, and then the final or maximum value of the force we need to provide as an input to the civil structural design engineer. I hope uh, this video making some sense. It is give some clarity about the short circuit force, or at the event of short circuit how the conductors behave. Okay, so today we are going to discuss about the short circuit force calculations. Short circuit force calculation means this kind of the event at the event, this kind of uh, the situations at the event of the short circuit. So for that what we do, for that we follow the 60865 standard that we are going to follow. So let me open that standard as well, so that we can use as a reference. So 60865. So for the short circuit current calculations, we use 60909 IEC 60909. But in order to calculate the effect of short circuit current, okay, the effect of short circuit current, we follow this IEC 60865 in order to check the effect of short circuit current calculation of effects, definition and calculation method. So this so definitions and calculation method we will follow this. So this IEC we are going to follow as it is, no any change, as it is we are going to follow, right? So in this 108 page, so we can see this English language only. So they have given this I will provide this IC standard that you can go through. So they have given the definitions, so please go through this definition as well. So I'm taking whatever the relevant page, so I'm taking that page from this IC standard, but I will request all of you that once you get some free time, please go through this standard as well. So this part of 60865 is applicable for the mechanical and thermal effect of short circuit current. It contains procedure for the calculation of electromagnetic effect on rigid conductors and flexible conductors. The thermal effect on bare conductor, so that we will also take the thermal effect. This one for cables and insulated conductors, the reference is made, for example, IC 60949. For the cable, again these situations will come, but for that there is a separate standard which is IC 60949 and 60986. But for the rigid uh, conductors and flexible conductors and bare conductor, this IC is applicable. Only AC system are dealt with this with in this standard. The following points should in particular be noted. So like you can go through all those things, and here you can see there's calculation short circuit current calculations should be based on 60909. So how much current will come, that we need to calculate based on 60909. But what we do in case of the substation project, instead of taking the 60909 calculations, we take the maximum grid fault level. So considering the maximum grid fault level, because as per these calculations the short circuit current value will be lower, but we have to take the maximum value of short circuit current that may come in the future, like after 10, 20 or 35 years down uh, line. So that fault current we need to consider. So for that, instead of taking this much value, this calculation based on 60909, we will follow the short circuit current based on the grid regulations or based on the country based regulations, and which would be higher than the value coming from 60909, this one. For the determination of greatest possible short circuit current, additional information from the other ICs may be referred. Example, detail about the underlying circuitry of the calculation or detail about the current limiting device if this leads to a reduction of the mechanical stress. Short circuit current duration standard depends on the protection concept and should be considered in that sense. So they have given some like inputs that you can go through, normal references. So this is their normal references. And terms and definitions: main, what is main conductor, what is subconductor. Subconductor, single conductor which carries a certain part of the total current in one phase and it's part of the main conductor. So sometimes we use bundle conductor, means more than one conductor per phase. So that other, in that bundle conductor, each conductor we call as the subconductor. Subconductor, then fixed support, and then simple support. Fixed and simple support, then connecting pieces, spacers. Spacer we use between subconductor to provide the required spacing. Mechanical element between subconductor, rigid or flexible, which at the point of installation maintenance, the clearances between subconductors. So clearances between subconductor we achieve with help of the spacer. Stiffening element, spacer, special spacer intended to reduce the mechanical stress of rigid conductor. Relevant natural frequency of CM. So short circuit tensile force FTD, in the maximum tensile force. Design value in a flexible main conductor due to swing out reached swing out due to swing out reached during the short circuit. So they are taking the swing, the force at the swing out angle, at the swing out position. Then drop force, uh, the maximum tensile force or design value in a flexible main conductor which occurs when the span drops down after swing out. So that is the meaning of the drop force. Then pinch force. Pinch force is the maximum tensile force in the bundle. So this is in applicable only in the bundle conductor. Flexible conductor during the short circuit due to the attraction of the subconductors, and due to the attraction of the subconductor, what force coming, so that force we are referring as the pinch force. So pinch force, then duration of first short circuit current flow FTK1. They have given many definitions that I request all of you please go through these definitions for the more depth understanding. Symbols and units, so they have, because they are going to use the formula, so in that formula they are using different symbols. So they have given what is their symbol, what is the meaning of that symbol, and what is their unit. So like CT, CF, CF is the form factor, CM, CTH, D, E, E factor, E, like that. There are so many symbols we are using in the formulas. So for that they have given here their meaning and unit here. Okay, so please go through this. I will take the relevant. I will take the relevant pages and relevant formula. General with the calculation method presented in this standard. Stress and rigid conductor, tensile force in flexible conductor, force on insulator and substructures, span displacement, heating of conductors can be estimated. So they have given here the formula that we will use, like formula 1, then like that they have so many formulas that we are going to use. Formula 2 that we will consider one by one. Okay, so this would be our reference standard. So we are today we are discussing the SCF calculation. This is very important calculations and very important point for the interview purpose as well. So please focus. So we are going to discuss about the SCF, short circuit force calculation. Short circuit force. Short circuit, the force generated are the effect of short circuit current are force generated by the short circuit current. So that we are referring as short circuit force. So SCF calculation. SCF calculations, and the reference standard would be IEC 60865 part 1. So that would be our reference. From this standard we are going to take as it is all the formula in order to calculate the SCF value. Okay, so in a simple way I have prepared my presentation so that I can explain it in a layman language and in a simple words apart from the IC language. So short circuit force calculations. So you can see over here that we have conductor. So conductor, so what is here, if current flowing in the same direction, then there would be attraction forces, and when current in the opposite direction, then there would be repulsion forces. So due to this attraction repulsion forces, like, there would be displacement in the conductors, and due to that displacement there would be force coming on this support structure. So that force we are going to calculate, so that this force we will provide to the civil engineer, and accordingly they will design the structure so that at this moment the structure should withstand and the structure should not damage. Okay, I hope the meaning of like why we are performing these calculations, the objective is clear, right? Let us see again. So why short circuit current force calculations, or why short circuit is required. So even though we have taken enough face-to-face clearances during the design to avoid the electromagnetic field of any phase, of any one phase to other phase, but at the event of fault, because here we have taken like my voltage, my insulation level, and insulation level again coming based on the voltage only. So accordingly,
Recording in progress.
yeah, Harasdeep. Now okay.
Okay, sir. Okay.
Yeah, sorry, there was some interruption on my side. Yeah. So back to this wise SCF calculation. So we are discussing, but at the event of fault, at the event, even though we have taken enough face-to-face clearances to avoid any EMF effect of one phase to other phase, but what will happen at the event of fault? There would be high current flow, which would be in the kiloampere. At the event of the fault, the short circuit current start flowing through the conductors, or we can say through the phases, and that current would be in the range of kiloampere. For example, like 25, 40, 50, or 63 kiloampere. So current, due to that current, so these short circuit current induce a huge electromagnetic force, and a huge electromagnetic force they induce, at the same time huge stress on the equipment. Therefore the SCF must be considered during the design stage for the safety of the support structure and the equipment as well. So SCF calculation is required to get the below informations in the substation design to find out the maximum short circuit force coming on the equipment terminal. So accordingly, I will take the equipment terminal terminal head accordingly. Second, to find out the cantilever strength of the equipment outer insulator, so that it equipment insulator should not break. Third, and most important, to evaluate the forces for the design of civil foundations and the support structure. Mostly the support structure, civil support structure. To evaluate the forces for the design of civil support structure. So in order to that, we need to calculate the force due to the short circuit current, and this short circuit current induce a huge electromagnetic force. that we are going to calculate. I hope I am clear. If not, let us see in other way. The forces are attractive. This short circuit forces are attractive when the current in two conductor flow in the same direction, as already we have seen. Whenever the direction of current are opposite, the forces are repulsive forces that we can see through this image. Therefore, to design the equipment support structure, tower, gantry, beam, we need to know the forces in kilogram or kilonewton or newton coming on the support structure in the event of short circuit, and the support structure should be capable of withstanding these forces. We also calculate the direction of forces. We also calculate the direction of forces and the maximum horizontal span displacement to check the adequacy of phase-to-phase clearances. Sorry, say again. Am I audible to all of you? Aditya, Akash, could anyone confirm?
Yes, yes, yes,
Yes,
yes,
yes.
it's
Yes,
fine.
audible, clear.
Fine, it's fine.
Yes, sir. Clear, sir. Clear.
Okay, okay. I hope I am clear so far why we are going to calculate these forces, right? What is the objective of behind this calculation?
Yes, sir.
Yes, sir,
Behind
yes,
this
sir.
calculation. Behind this calculations. Okay. Behind this calculations. Objective. Kilonewton, yeah. KM is kilo. Okay. Okay. Forgive me, it is wrongly mentioned. K small and capital. That's fine. Okay. Now let us see what we calculate. What we calculate and why we are calculating that. Who telling us to calculate that? So the IC 60865 standard provide the calculation formula, and as per the method described in 60865, the below type of forces need to be calculated under the short circuit current. Force calculation: tensile force during the short circuit, tensile force during the short circuit. Okay, during the short circuit, during the short circuit, tensile force after the short circuit. After the short circuit means conductor now coming back. So when they are coming back, then again there would be some forces. So that that force value will be very minimum, but we also consider this in the calculations. Okay, so tensile force after the short circuit, maximum mainly the tensile force during the short circuit, but when the conductor dropping back, then at that time what force coming that we are calculating, that value would be lower that than the tensile force during the short circuit, but we consider this in the calculations. And third is the tensile force due to the pinch effect. Pinch effect means, this is just the terminology, pinch effect or pinch force, and this pinch force would be applicable in the bundle conductor. If you have single conductor, then no need to perform this calculation step. Only step 1 and step 2. In case you use the bundle conductor that we use for the 220 kV and 400 kV substation, most of the time we use bundle conductor. So at that time, this pinch force will come in the calculation. So what happen actually pinch force? In case of the bundle conductor means more than one conductor per phase. That the bundle conductor means two conductor per phase. Two run. Like you can see over here, if it is clear, A and B. So in per phase, in one phase, I am using two conductor. Why I am using two conductor? To support the continuous current and to support the short circuit current, right? As we have done the bus bar sizing calculation in module 4, right, about the conductor, about the bus bar, about the conductor selection, isn't it? Like we have discussed whether we require single conductor or twin conductor. So twin conductor means two conductor per phase. So now if I'm using two conductor per phase, and between that, even though I have used the spacer, but what will happen when the short circuit occurred, the conductor clash to each other. Now you can see here conductor clashing, conductor clashing, conductor clashing. Here again, due to the clashing, like they are provide like providing the force or load on the their supporting point are where we have done the stringing or the support structure. Result the pinch force. Result the pinch force. You can see over resulting in the pinch force H that you can see that we have calculated over here. The pinch force resulting where we have done the stringing at that point. So the maximum, so this three and out of three, which one is maximum? That one value we provide civil that this would be the force from the electrical side that will need to be considered for the structural design. The maximum force out of the above, out of three, the maximum are considered for the equipment support structure design. Okay. Now let us see one by one. Let us see one by one. So what is the meaning of those? So the first FT means the force produced by a conductor swinging out during a short circuit. Conductor swinging out. The conductor swinging out during the short circuit. Conductor swinging. You can see conductor swinging out. So due to the swinging, whatever the force coming, that I am telling as a tensile force. Tensile force due to the conductor swinging during a short circuit and a short circuit tensile force. In the conductor there will be sag. Like here it was the tubular conductor, so there was no any sag. But in case of the flexible conductor, there would be sag in the conductors. There would be sag in the conductor. So at the midpoint where the sag is higher, at that point swinging would be higher. So and there at the midpoint in the conductor, the midpoint there will be sag. Midpoint there will be maximum sag. There would be sag, but at the midpoint that sag would be higher. Why sag in the conductor? Due to the self weight of the conductor. Due to the self weight of the conductor, plus the gravitational force of due to that the sag coming in the conductor. So in the event of short circuit, the conductor will swing along. Not only swing, they will also oscillate. Not only swing, they will oscillate. So the tensile force in a flexible conductor comes oscillate. So we have to calculate what is my oscillation, what is my like. First of all, there is two force, the like electromagnetic force and then force due to the gravitational, and then we have to calculate the ratio, and then we need to calculate how much swinging occurring. That all we have to calculate one by one. So we need to calculate the static conductor sag. Sag we need to calculate the sag at the midpoint. Sag at the midpoint. Sag at the midpoint. So if I'm this Excel we are going to follow, and whenever you will work in a company, you will get this Excel template. Each company who work in the substation or in the TND, they have their own like designing Excel sheets. So when you will work in a company, you will get these kind of the template. But here we are discussing so that when you are getting this template, when you are doing the job, so how to provide the inputs in that template, and what calculations you are doing, what like how we need to perform, and like from where we will get the input value, and like the meaning of all those calculations, all those steps. So this is this Excel we are going to perform, and in this Excel all the formula I have taken from the 60865. From this just copy and paste over here and just put the value over here. So if I go to this, so I'm there are a lot of steps I'm doing. That one by one will take the steps. Like if you see here, period of conductor oscillation, so that we are calculating the oscillation period, and then we will calculate the sag as well in the conductor, that how much sag coming in the conductor. So each one by one we will do this, how much sag coming in the conductor, that we will also calculate. I will come later on about this Excel. So oscillation, stiffness, stiffness we need to calculate. Conductor swing out angle during and at the end of short circuit, and finally the tensile force. Then after doing this, then finally we reach to the tensile force calculation, FT calculation. Okay, tensile force calculations. And then third is in here, third is the second is the drop force, tensile force after the short circuit, FF. Tensile force after the short circuit, FF means my drop force, FF means my drop force. At the end of short circuit, the conductor drop back, so the tensile force in flexible main conductors caused by conductors dropping back after the short circuit is called as the drop tensile force, or FF. Okay, third one is the pinch force. The tensile, this one is meaning of this force is tensile force developed in a bundle of flexible conductor due to subconductors attraction and repulsion in the self phase bundle of conductors is called pinch forces. I have taken, so this is one way to understand this, the meaning of FT, FF and FI, what the calculuses we are doing. Another, along with that, you can also refer this 60865, in that they have also given all the definitions. Okay, so you can also refer this. I have taken there, but some modifications I have done just to properly understand drop forces or short circuit tensile forces, pinch forces, bundle flux, short circuit due to the attraction of, like here that like that, but some small modifications I have done just to make it clear. So finally, the maximum value of FT, FF or FPI shall be selected as a short circuit force on the supported structure. So if you look at this section, and if I go back down, so all three I have all like three, that out of three is two calculated. We will see that why two calculated, because there was some if and but, like there is some clause in the F of calculations. So then we will see that, and out of that two maximum, which one is the maximum, that value we are taking for the as for final value, and that value will provide to civil engineer for the structural uh, design. Okay, now let us see one by one. So what I'm trying to do, I'm just trying to take the 60865 the extract and trying to explain this, but we will perform on calculation as well. So if we go, the first step in the calculation, the first step in the calculations is the like electromagnetic force calculation, electromagnetic force calculations, equation 19. So the characteristics of, and like here you can see flexible conductor arrangement. Here all again you can see whatever we have discussed, that you can see that written here in 60865. So the characteristics of electromagnetic load per unit length and a flexible main conductor is in three-phase system is given by F dash mu naught divided by 2 pi 0.75 IK 3 dash squared divided by A LC divided by L. So all the formula we are going to take, and in that formula we are putting the value, and then we are calculating this SCF. Okay, let us take what the inputs we required to carry out the SCF. So to carry out the SCF, we will be required below input data like the short circuit current, because we are calculating the effect of short circuit. So obviously we require the value of short circuit current and the duration, whether 1 second or 3 second. So that value. Second, what is the R to Y and Y to B phase spacing? Phase spacing, span length between the conductor. What is my span length? Span length means length between two supports. So one support over here of the conductor and second support here, second support like here. So what is my, between two support, what is my conductor length? So that length sorry uh, so that length, span length, for which SCF need to be calculated. Conductor type, what conductor I'm using, what is their diameter, and the conductor construction parameters, such as the conductor yield point stress, conductor diameter, conductor modulus of elasticity. Okay, so this all input we required, and then we perform the calculations. And so this short circuit current value will take based on the voltage wise, that what voltage, and corresponding to that voltage what the short circuit current we are taking in the durations, that will take phase spacing from the layout drawing, span length again from the layout drawing. Like yesterday we have discussed about the span for the 400 kV, the support we provide after every two bay, right? And each two bay, and each bay length how much? 24 or 27 meter, right? Right now. So two bay means of 48, right? 48 if 27 then 49, like that. Hope I am clear about the span length. For 220 kV after each 3 bay, and 1 bay 16 meter. So 16 into 3 means 48, after again 48. So it means you take your layout and then take which portion you are doing the calculation and what is the span length. Span length is changing, so you have to perform the different calculations for the different span length. This is one way. Second way, you can take the maximum span, and for that you can perform the calculations, and that value you can apply for rest of other structure as well if you wanted to not doing all the calculations. So either go with the higher span, or recommended is that take all the respective span and accordingly to the design, because if span changing, then SCF value will change, and accordingly you will design the structure so that there would not be any over design in the structure. So it is why recommended span wise we need to perform the calculation. So span length for which SCF need to be calculated, and then conductor type.
This span is for total length, right? I mean,
Support length between the
three
support,
supports.
length between the support. This is one support here, next support over here. So this is my one span.
Okay.
One support here, next support here. Is it visible? This drawing is visible. One here, second here, right? Say yes or no. At least say
Yes,
no
sir.
if not visible. Nah,
Yes,
do
yes.
not take consume time. So this is your one span, right?
Yes, sir.
So
Yes, sir.
like that you will have multiple span. So multiple time you have to do. Like what if identical span, then no need to do. But if span changing, then please change the calculations. And that is very easy because each and every company have the template. So only you have to update the span length only, and automatically you will get the value of the tensile force. So it is not very hectic job, that can be done only span length to be updated in the Texas sheet. Okay, clear what is the meaning of a span? What is the meaning of a span? Clear? Span length clear? Clear or no? Or
Yes,
not?
sir. Yes,
Yes,
sir.
sir. Yes, sir.
Span length for which SCF need to be calculated. Conductor type means what conductor I am going to use, that all. So this is required. So this is all theoretical concept. Let us take the 60865 and let us do one calculations to understand the overall process. This calculation would be lengthy. Okay, so please do not worry about that if it is lengthy, because the formula coming from the 60865, and in that formula there are so many constant, so that constant also we are calculating. So when you will work in the company, you will get that Excel template, in that you have to use that template. But here you learn that how to do that calculations, but so that when you work on the project you will have the conceptual knowledge, and independently you can perform the calculations. And secondly, like during the interview, if anyone asking you, tell me about the SCF calculations, why we do, what is the input required, and what is the steps to perform the calculations. So that knowledge also, obviously, you will get that knowledge. Okay. So so let us take. So I'm taking one of my project example for the SCF calculations. So here it was a 500 kV substation. 500 kV substation is identical as 400 kV substation. In India 400 kV, but in some countries, some in Middle East country or some Russian countries, they have 500 kV voltage also. So I have worked one project which have 500 kV substation, same as 400 kV. Each and everything we designed same as 400 kV. Okay, so this is my line side, and in 500 kV same we have followed the 1.5 breaker scheme. So this is my line side country. Hope you are understanding about this layout and this portion. So I have taken one small span or one small section from the layout drawing. So in that I'm just taking 1.5 breaker scheme. So my main bus taking the drop from the main bus to the equipment like this connector, then breaker CT. Like you can see yesterday we discussed same layout, then going up here, and then with help of the jack bus, then going down with this connectors and then metering CT EMBT because it was generating power plant. So that is why near the point of connection we have used separate metering CTVT. It is required by the client, separate metering CTVT that we have provided here, and then wave track, and then here we have connected with the transmission conductors, and here we have the CVT and surge arrestor. So we have taken the drop for that. So for here like I have the span bit from this to this, it was around 49 meter from here to here. Hope you can understand the study discussion. In one diameter we have 3 bay, so 1 bay here I have taken.
दाल चावल ही बनाया खाली
Keep muted यार if you have any background noise.
7 बजे तक खा लेंगे
Is it clear? This layout is clear?
Yes, sir.
Ritesh?
Yes, sir.
Okay. So now here the span length. So what we do when we perform the calculations in the layout, different we mark the span length. So here I have marked this span length. It was coming 49 meter. So from the layout I took the span length 49 meter. So this is one input that we are taking from the layout. Second input that we required is the short circuit current value and duration. So this will be based on the project technical specifications. What is the short circuit current and their duration? So my voltage, nominal voltage and rated voltage, then short circuit current and their duration 3 seconds. So we need short circuit current and duration as an input to start the calculation as the of the SCF, as the SCF will depend on the short circuit current. So we need this value. So I'm taking, so for 500 kV the grid short circuit current was 63 kiloampere. So I have taken 63 kiloampere, and instead of taking 1 second they have considered 3 seconds, which is not the usual practice. They should be 1 second, but they have taken higher side due to just some design margin. So anyway, whatever given in the design specifications, technical specifications are client requirement that short circuit durations 3 seconds that we have considered. So here we have taken as 3 seconds. Okay, then yeah.
Sir, the IC mentioned is 865 or 060 865 over here. Calling calculation are based on
Same. Actually, what happened?
same.
Instead of quoting full name, most of the time we quote their short name. So short name is 865
Okay.
because 60 is the series. Okay,
Yes, sir. Yes, I understand.
60 series, and of that 60 series, this is 865.
Okay.
Okay. 61936. So instead of taking 61, you can say 936. This is the series of 61. Okay.
Okay, understood.
Okay. So 60865 means 865 in the short. Okay. So then we require the conductor parameters. What conductor I'm using? Because we need to know about their elasticity factor, about the Young modulus. So we need to know about the conductor. So that for the example, we are considering the main bus bar flexible conductor here in that project, and we will calculate the short circuit force on towers and gantry. So on the tower and gantry here, on the on this tower and gantry. On that we are going to calculate the short circuit force. So I'm taking this conductor which is 4 into ACSR quad. ACSR 650 is the conductor type. So I'm taking this conductor. So this conductor parameters I have asked from the conductor supplier or manufacturer. They have given me. So that value I have used here. Like my conductor type. Conductor type is based on my conductor sizing calculation, right? Busbar sizing calculations, right? Okay.
Yes, sir.
So conductor type is my choice, is my selection, as we have discussed in module 4. Okay. Number of subconductor, it is my choice that how many conductor I am going to use as per the required continuous current and short circuit current, as we have taken in the module 4. This 2 is my value corresponding to that conductor that we have selected. Corresponding to that conductor, I have asked from the conductor supplier to give me the conductor weight. So mass per unit length of the conductors, the cross-section area of the conductor, the Young modulus of the conductor, this one in centimeter, then converted into the Newton meter, it was K centimeter, and then diameter of the conductor, and then material constant. So this all I have taken from the conductor supplier. This 2 is my choice. Like that, I have, this is a different conductor that we do not use in India. In India, what conductor we use generally? ACSR, Panther, right?
Yes, Panther,
Zebra, Moose,
Moose,
Persimmon, sometimes Tarantula, very less, sometimes
Zeb, Zeb, Zebra.
Zebra here. Okay, so for that, what conductor generally we use in India, for that I have make one table for your ready reference. But I request you to verify this from the supplier. But if no values, then you can take this value as well. So mass per unit length of the subconductor means one conductor, mass per unit length. Okay, subconductor means one conductor. Cross section area of one conductor, Young modulus value in K centimeter square and Newton meter square, and diameter for the panther. Okay, similarly for the zebra, their area 484.5, 28.62. For the moose, their area, okay, and their diameter. For the Bersimis and Tarantula, here is my SSR 650 that I have used here. Okay, so what I selected? I selected selected means what I was using CSSR. So here I have used this SSR 650 value over here. I hope this table is clear to all of you. Now, in this calculations, we are going to use the Greek word. All the calculations, if we refer the 60869. Yeah.
We are selecting 4-number conductor, but we have only 3 phase, na?
Yes, sir.
That is not clear.
4-number conductor per phase, sir. 4 conductor per phase.
Okay. Each phase 4 number, right? Okay.
Yes, sir.
Sorry.
Each phase 4 number.
Okay.
Okay, sir. I'll show you, sir. Could you see here? 1, 2, 3, 4.
Yes, it is clear now.
Yeah. Okay. Okay. No worries, sir. No. Yeah. Now. Uh, yeah. What I was discussing about the conductor manufacturing parameters. Now, second thing, that in the calculations we are using many Greek symbols. All the calculations, like it is a Greek symbols they have used. If you see here, mu naught. Okay, so mu and all, most of the time, maximum symbol that we are using, that is the Greek symbols or Greek word. You can see over here all the Greek word coming. So in order to your ready reference, and for your ready reference, I have prepared a slide so that when you are uh, doing review the class, or when you are performing the calculations, you will know what is the name like this of the symbols that we are using here. Okay, symbol that we are using here, like alpha, beta, gamma, delta, epsilon, theta, eta, theta, kappa, lambda, mu, nu, then g, omicron, pi, rho, sigma, tau, epsilon, phi, chi, psi, omega. So these are Greek alphabet used throughout the calculations. So if any Greek word alphabet if I wrongly pronounce, so please refer this page to for the correct name. Okay, so all the alphabet in the calculations would be the Greek alphabet. Now in the Excel calculations we need to put all the inputs. So here we need to put and we need to put the conductor, and about the conductor span. If we look at this, what happens, as we discussed yesterday, the conductor span we take center to center, from one center to other center. But if you look at this beam this beam have certain width, beam have certain width, okay, width, and that width is generally 2 meter. It is a general uh, uh, width size. Additionally, if you look at this, what we are doing, this conductor stringing we are doing with help of the tension insulator, right? So if I need to calculate the conductor length, so what would be the actual conductor length? Total span, right? What would be the actual conductor length? Total
Right.
total span minus how much minus? How much minus? First of
Minus
all, first of all,
both the side of
yeah.
Both the
So
side
string.
of
yeah,
insulator and structure.
minus string distance.
tension insulator.
yeah. So let me return here. The span length as per the discussions we take center to center. So as per the layout drawing, it was 49 meter from center line of one, this center line of one gantry to center line of other gantry. So in this is my span length, but what would be my actual conductor length? Actual conductor length. What would be actual conductor length? Means then we have to take total span length which is 49 meter, then minus half this beam, and on the opposite side also half beam, right? So 2 into 1 by 2 of beam width minus this insulator both side, 2 into insulator length, right, insulator length, this one I have to minus from this side and the opposite side also, this side as well, isn't it, right or no? Right, so what would be my actual length? So if you see here, this insulator length of the string insulator along with the hardware, it was 8.73 meter, quite high length, 8.73 meter, this length, because it was 400 kV. So that is why along with the support hardware, this was a quite long support insulator. So 8.73 one side, so two side, 2 into 8.73. So what would be my actual conductor span? So total length 8.73, conductor span 49 meter, conductor span, conductor L means total span, LC means my LC stand for the chord means actual. So total actual length would be 49 calculator, 49 minus 8.73 minus again 8.73, right, minus 2 I'm taking half of the this one beam girder width, so 2 meter this side, you are getting my point, right? 2 into 1 by 2 of beam width. So 2 into 1 by 2 means this 2 cancel from this 2 means any one side beam or girder width we can take, so greater, so that also minus. The actual would be, even though it was 49, but actual coming 29.55 or 30, you can say. Clear? This it is enough. Anyone could confirm?
Yes,
Clear?
yes, sir. Yes, sir.
Now,
Yes, sir.
now here I am taking tensile force, static force, static force, static force, 4000 kg. Actually, what happens, as per the usual engineering practices, initially one static conductor tension we take, and for that we take 1000 kg per conductor, and I think same we can check through the PGCIL, PGCIL. If we go to power grid erection, switchyard erection specification, in the erection specification they have also given switchyard erection specification. Switchyard erection specification. Revision 9 might be, could be more revision, is revision. Technical switchyard erection. Switchyard erection. This is one grid erection specifications for the like hardware and other lot item, not the main equipment item, but other like earthing conductor, insulator, uh, flexible conductor, tube. So for that they have given some standard recommendations. Like if you can see here for 400 kV. So and they have given here the short circuit forces as well. Short circuit forces and special weight, special span for 765 kV, 400 kV gantry structure. So we are taking 500 kV, which is equivalent to 400 kV gantry structure. So now what will happen, as I mentioned in the beginning, for the power grid project they have already given the SCF per phase, so we need no need to calculate, we can take this as a reference and we accordingly, like we can do further civil calculation. But in case of others we need to perform, but for that again the static tension, for that we can take this reference as well. So normal tension SCF per phase we are going to calculate. Okay, and fault level 40 kiloampere. So corresponding to that 40, 50 and 63, my SCF going to change. You can look at this. Okay, not drastically change, but a little bit it will change. And here if you see, everywhere normal tension is 410. 410. Okay, 410 means 410 here quad conductor. They have not mentioned that it is for the quad conductor. Yeah, here mentioned a quad conductor, quad ACSR. 410. Twin ACSR, since the span was high, due to that reason they have taken 410. Okay, and this is
Sir, one question. Actually, this 4 ton, from where they are taking this 4 ton?
this is like some initial assumption we can say, or some based on that conductor uh, weight
Actually,
without.
sir, if you are going to consider the conductor weight, then I think conductor weight to 2 point something kg into the gravitational force 10 multiplied by, accordingly they are taking.
Might be, I need to double check, but might be this could be one background for that.
Same, we are also we will consider 40 for our calculation.
In your company as well, right?
Yes, sir.
Yeah, as I mentioned, I will check this with this. So what you are doing? You are just taking the conductor weight, right? So
Yes, sir.
kg per meter
Kg per meter weight. Yes.
into
Into
span,
G gravitational force 9.8 or span.
span
Yes, span
length into meter.
into meter into gravitational force G 9.8
Yeah, 9.8.
and multiply by conductor. Suppose we are considering quad, then multiply by 4, otherwise 10, then 2.
2. Yeah, like that. Yeah, like that. Here we are taking, and this is your normal normal
Normal tension.
tension,
Normal
yeah,
tension
normal tension,
or normal load,
yeah,
yes.
normal load. So like that. So taking that, just taking the conductor weight, there this tensile load, as I mentioned, this is taking the normal conductor weight, normal load. Initially, they have taken that will come on uh, the country structure. Okay, so this, yeah, taking this reference, same, Ritesh, same one. Taking, because here also you are using the conductor detail, conductor weight per meter length, right? Conductor weight you are taking also here, conductor kg per meter you are
Yes.
conductor
Sir,
weight.
a small thing over here. Are we? Is this? I mean, is there some gray area, but between the work pulling tension of the conductor and the weight of the conductor? Pulling tension of conductor and weight would be different, isn't it, sir? I'm just trying to
Yeah,
understand.
pulling tension means that the pulling
No, in
tension
this in
will,
this table, what is mentioned as 4 tons would be the pulling tension at which the cable would be the conductor would be maintained,
yep, the tension which is coming on the gantry structure, that tension. So
not the conductor. Achha,
yeah, not the
I mean,
conductor
Actually,
means,
no. Actually, sir, this tension is also applied by the conductor and then due to gravitational force
yeah,
on the
no, no.
gantry
applied by the,
structure.
applied by
I
the,
am only trying to understand. I am only trying to understand whether the gravitational pull causing a tension pull on the gantry is one
yeah,
that is due to weight,
due
and
to,
second one is the conductor itself being pulled into the tightness so that the catenary is reduced. That
Mhm.
is what I am referring to. So, which is appropriate, sir? This 4 ton is appropriate for what? For the
appropriate
self weight or
appropriate
the
sir,
pulling tension?
appropriate that, like, let me go to again view, appropriate to that, how much tension coming on this gantry, that that 410, how much tension coming on this gantry. And so for that I'm taking both. You can add your conductor weight, your conductor weight here, sir, your conductor weight, and plus
Yes, I am hearing.
conductor weight, and plus, like, you have the turnbuckle, like, for that, through that you are maintaining the tension at one side.
Right, right. So that is exactly what I'm trying to understand. That 4 tons corresponds to the not the weight, the tension of the conductor. That is
Yeah,
what I'm
but
trying to
that,
understand.
tension, in that tension, your conductor weight is automatically considered in that tension, because that tension means the force. So this force is coming due to conductor self weight plus the gravitational,
Right.
plus the force due to the gravitational on the conductor. So in that, the conductor automatically considered here, sir.
Right, sir. Okay.
Yeah.
Okay,
So
sir. Okay,
means
sir.
what the force that coming on this support structure initially without short circuit, just my static without short circuit. Okay, so that I'm taking as in, so general practice that we take, general practice, it is general practice, and for that practice I prefer this power grid, that we take 1 ton per phase. So if I'm using quad, so like 410 total, including all four. Twin here, but again I'm taking 40 because my span length was quite big, 70 meter. That was the reason. Then again quad 410 70, then twin, but again 410 I'm taking because again conductor length is, span was quite long. That is why even the 210 we can consider because twin conductor, but since my conductor span long, so I'm going with the 410. 48 meter, then 410, 52.5, all those things, quad 410. And here twin also I have taken the 4 because again 52.5 span was not the small span, 50 meter is very long span. We have taken, this is my normal tension. My SCF will change corresponding to my span, but this normal tension that I have assumed a static value initially. This is for 400 kV. If we go to the 220 kV, then generally we take 210. So if we go to any 220 kV, so for twin conductor it is 210. Quad means again 110 per conductor. I'm taking same concept here as well. So quads 410. So 410. So if you see here span same 44, 50, 54, 54. Quad 4, but twin then 210 here. Okay, twin quad. So this is a reference that I'm taking, for the quad conductor 410 as an initial normal tension on the gantry. Normal tension on the gantry, the 4000 kg tension of the conductor. So here tension of the conductor. So now this is in the kg.
Hello, sir.
Is it okay?
Here,
Yeah.
here for the tension of conductor, isn't we perform first sec tension calculation
Yeah, we perform.
and based
Yeah,
on the value of tension
yes, yes,
we have obtained
we
here.
perform say the sec tension calculation. But
Also,
what?
in the later stage when we
Yeah,
calculate
yeah,
FES,
perform.
so the value of sec
Yeah, yeah. Sec. I understood your point. Yes.
which obtained in the sec tension value,
Yeah.
so we have to consider that sec value in the FES.
Yeah. So what we do? We
So
perform.
the initial first stage, isn't it before SCF we have to calculate sec tension first,
Yeah. So we perform sec tension.
and based on the sec tension values
Sec.
result.
Let me come here. Let me speak.
Okay,
Yeah, you are correct.
okay, sir.
You are correct. We perform sag and tension calculation. Okay, so this is not only one input that we need to provide the civil to design the structure. Along with this input,
Yes, sir.
sag and tension also to be calculated, and that also to be performed, to be provided. How much the tension coming on the conductor. But in
Yes, correct.
fortunately for that sag and tension calculus, again we take this. Again we have to consider the static tension. Okay, sake. So for that static tension again 40
Yes,
and
sir.
4000 kg you have to assume. This again same we take. And
Uh,
then on
no, sir.
different.
Generally, we are.
Okay, you
Sir,
continue. Okay.
complete yours,
No, no, you
please.
continue. You continue.
So generally, for the sec tension, we are performing from the standard IS 5613, and for the initial tension, we have to get the value from the IS 802, and in that IS 802, there is a uh, defined for the initial and static tension value.
Yeah, okay.
How we can obtain that?
Yeah. Yeah, okay, yeah. Fine. Yeah, okay, continue. Okay, I'll take any sectors and calculation again. If I have, I will. Anyway, this is the discussion due in the uh, transmission line model. In that, we will discuss about this. Okay, this is one sectors and calculation. Say, okay.
Yes, sir.
So conductor. So this is my input for the sectors and calculation. So conductor, I'm taking Bersim is subconductor numbers and spacing. Here I'm putting subconductor per phase and C. Then height of the span length, design tension 2000 here.
Yes, sir.
Per conductor design tension not to exceed 25% of UTS ultimate
Tensile strength.
tensile
So the
strength.
value of this given in the standard IS 802.
Yeah. So if you look at this two conductor and for that 2000 kgf, right? So per conductor
Yes,
1000
sir.
kgf.
Correct, sir.
Okay. Either we can check the IS 80.
Sir, can you open IS 802?
Yeah, you
What is
can, yeah.
in that?
Sure.
To,
So I have IS 802 that also. So yeah.
so uh, on the 15 number, tension limit is given.
Yeah.
Go down.
So this is zone wise wind speed that already we
Yes.
covered that zone wise the civil will take the wind, they will calculate the wind force. Okay. So wind load here, wind load they can calculate taking this then wind load on the insulator string. Okay.
Clause number 15.
Yeah. Come. Safety here.
Yes, 15. Yes. Here the condition is given.
Yeah. So conductor ground wire tension at everyday temperature and without external load should not exceed the following percentage of the ultimate tensile strength of the conductor. Initial unloaded tension 35, if final unloaded tension 25%. Provided that the uh, ultimate tension under every temperature and 100% design wind pressure or minimum temperature and 36% design wind pressure does not exceed 70% of the initial ultimate tensile strength of the conductor or ground wire, not for 400 kV and 800 kV, then the final unloaded tension, ultimate tensile, okay, all those things. And then double triple circuit, quad circuit suspension tower, large. Yeah, anyway, they have given whatever they have given here. So I think.
Yes, so based on this condition, we have to perform first set tension
Yeah.
according to the initial and final.
So what I'm telling, so I again go back to sag tension. So in the sag tension again, max, like I have considered one conductor static tension,
Yes,
which is 2000 kg. So first I have taken one static tension, and then again on different temperature I am calculating the tension and corresponding sag.
temperature.
Yeah, temperature wise. I have one static tension.
Correct, sir.
Okay.
So,
Might be you can correct me. Might be you know some alternative method. So you can interrupt me. So like.
so generally for the TL, we are performing from the PLSCAD software.
Yeah.
But however, for the substation set tension calculation, we have prepared Excel sheet, and according to
Yeah.
that, we can obtain
Of
second tension value. And
second
there,
tension.
second tension value we have incorporate in the short circuit force calculation.
Yeah. Yes. So like. So in short circuit force calculations, how you do, like in your company, how you perform? So first you perform SCF. So which tension then you consider?
Sir, final tension. Here we can two cases for initial case. If my conductor is twins, so we can obtain 2000, as you said earlier.
Mm-hmm.
And for the 75 degree, whatever the value which comes in the sec tension value, so we can consider that tension value for the 75 degree temperature
1 second. So
or 85.
let us look at here. So initial condition, final condition, stringing chart. So here I've taken 85 instead of 75. Okay. And then my initial conditions to 2.5 kg. Okay. Conductor weight per meter, wind force, loading factor, and then initial conditions, and at 36% is 0.36 here we have mentioned here. Okay. Check for design conditions, wind factor, and then initial tension that already we have taken 1000 kg per conductor, and then initial stress, according to that we have calculated the initial stress, the stress initially corresponding to that tension, and then calculated tension per conductor 929.79 kg. Okay, so this is your final tension,
Yes.
right?
So yes,
Okay.
yes, sir.
So
Correct.
if you look at this value not going to very much change with the whatever we have taken 1000 kg. What I was telling that I can put.
Understood, sir. But the
Yeah, okay, fine. Yeah, I'm not denying you. This is also you can go. This is also one way. You can go first. You can calculate the final tension. So this tension value you take and then you put here in the calculations. Okay, say. So I agree with you. That also we can do.
yes, sir.
I uh, if I look at this, so I think I have noted here the tension of the conductor. I have taken 4000 kg, considering 1000 kg per phase, per conductor, sorry, per conductor. So 1000 kg per conductor. I have 4 conductor per phase, so 4000 kg per phase. So this is one way, and then kg converted into the Newton, so we have to multiply by the G, by the 9.81, so we can convert kg into Newton. So it is coming 39,240 Newton. So this is method A, and as you mentioned, instead of taking this one, we can first put the span length in my sag tension calculations Excel, then whatever the tension coming, final tension coming, so based on the temperature, that also we can put there. Like here in that case, that would be, instead of 1000 kg, that would be 929.6 kg and 930 kg. Okay, this could be also one method. Okay, thank you, sir. Thank you for
Then we have to
yeah.
apply on the FES when we calculate FES. So generally FES formula is given in the standard IS 6065 page number 28. But if we calculate sag tension value, so according to the value of sag, we have to obtain FES value in the later stage of SCF calculation.
Yeah. So which standard say? IEC
60865, whatever you have opened.
Okay. 6065. Yeah.
On the page number 28.
Okay. On page number 28. Okay. So 19 and then 30.
Question number 22, I think so.
Okay. Okay. We'll see. Page 27.
Below, sir, below.
Yeah. So which one you are referring?
Page number 28.
FCS.
28. Page number 28. Yes, FES.
Okay. Yeah. The equivalent static conductor sag at midspan is given by. So FES, yeah, and M dash GL 8 FST static.
Yes. So here also we have to obtain by
FES will give you
sag
the
value.
sag value. Okay. So yes, sag.
Yes.
So what I'm doing here, the sag value I'm calculating. So in this section, like here, if you have taken this FES, this is my stress. This is my stress, and then after that stress swing, and then yeah, because in the sag might be we have inserted that. Okay, so FES you calculate here in the sag tension calculation, where you calculate.
Yes, based on the value of sag, we have to put that value in the short circuit force
Yeah.
calculation.
So calculation, clear span, design, conductor. This is conditions. Then weight for sag conditions. Okay, when to force on conductor permitted, loading factor, checking for worst conditions initial and check for design, stress, and then tension, and then stress, and then final apparent sag, and sag for the calculations. Okay, anyway, calculation for sag for calculated tension. So I have used another formula. I've used another, like this formula I've used here.
Okay.
This formula I've used here in order to find out the sag. Here, A into sine h dash string length divided by A. This is one method, but whatever you are telling, that method, that formula whatever the formula you are referring, FES, that formula I use in my calculations, I use in the SCF itself. So if you go in this formula, say, you can see I have used this FES. So I have calculated this. Here is your FES. So sag that I am calculating, and then I I have used this FES here in this. What is the FES? Okay, slack conductor. Then gamma factor string. It's quite big calculations. And then yeah, you can see FST here. I'm taking the FES also. We ES. Let me again see what the FES that I have done this. FST, NSP, SWSG. So F, it is my electromagnetic force, and then resultant mass. Okay, so ratio that calculating, and then direction of force, equivalent static conductor sag. This is the sag at midpoint.
Yes.
So this is your like FES you are telling, I'm telling some in other way. Okay, so
Okay.
and dash S. So I'm putting same formula, but I have used this symbol BC to calculate the equivalent static conductor sag at midpoint. BC is my FES. Okay, equation 22 you have referred now. So same equation I have referred here. Okay, so n into m dash s, so n into m dash s into g into L divided by 8 FST that we have just taken 4000 kg r in the Newton 13.420. So FES I'm calculating over here 0.7 meter. This is that I'm doing.
Yes. So generally, we have.
Yeah.
Yes.
Yeah. This.
Thank you for clearing the understanding.
No, that's fine. Yeah,
Sorry for
that's fine.
disturbing
Yeah, no, that's
in
fine because
between.
might be a few every company have their slightly change in the calculation approach. Okay, so might be you are taking FES from the sag tension. Okay, and you are putting here as an input,
Yes.
right? In my case,
Yes.
what happened? FES I'm calculating itself in this Excel. In this Excel, FES I'm calculating, which is I have noted as BC, and then based on this BC, I'm just calculating the conductor oscillation period, and based on that oscillation, what is the then resulting period of conductor oscillation during the short circuit current flow, and then taking this T resultant divide by T ratio, then we take that this formula, then actual angle modulus, and then this stiffness norm also we have to calculate, and then thereafter swing out angle, and uh, uh, then like how much swinging have occurred, so that swing out displacement distance, like here it is psi, so psi value 0.6 meter displacement occurred, like as we discussed that there would be displacement in the conductors, that how much displacement occurred, that we are taking, then swing out angle we are taking, swing out angle, then taking that displacement and swing out angle, here we are calculating the short circuit tensile force. So there is two conditions, based on that we have to select the formula. So if my tk1 is greater than t resulting oxidation divided by 4, if it is greater than tk1, this formula, if less than this, so this formula. So t resultant by 4, it is t resultant 1.5, which we calculated earlier, then divided by 4, which is coming 0.376. So TK1 is was 0.629 that we have calculated in above step. So 0.629 is greater than 0.38. So it means we have to take this formula to find out the tensile force. So 3 into R. R is the ratio of my electromagnetic force and the tensile electromagnetic force and the gravitational force. So this ratio R that we have calculated. So one like R we can see here I'm taking the value of
Hello, Jacob.
yeah.
Sorry to interrupt you. Because of this conversation before, so we just confusion about how to start from there. Could you please start from
Kinchan,
the
I will
after
start from the
input?
beginning. Yeah,
Yes.
I will start from the beginning. Okay, and don't worry.
Yeah,
I
yeah.
understand it because
Because it's about this conversation. Like you are going to the another page again. You are coming this page.
yeah.
So
I
I'm
will
just confused
no
about.
worry. I will start from the scratch again. Okay, don't worry at all.
Okay.
Okay, I'm just like because he also worked as a design engineer in some company, so he has done some alternative approach. So we are just validating his approach and my calculation Excel. That's all that we are doing now. Okay, fine. Okay, no worry. Let us start from the scratch again. Uh, so back to the calculation. So back to the calculation. So again, what the input we require that we have listed here, It is clear so far, Kinchan. Input is clear to you, right? From where to select the value, from where you
Yeah.
need to select the value that the input value that also clear to you, right? That also clear to you. So let me know if anything not clear. So again starting from
Yeah.
the beginning. So yeah, so we calculated the conductor span length. So this formula we apply total span minus 2 into stringing insulated length minus 2 into beam arc entry width. This one is clear. So 29.55 is clear, right? So we are here actually
Yeah.
tension. We are discussing about the static tension. So static tension like
Sir, how can we know the beam width before this calculation? I mean that based on the calculation only we are deciding the beam width and the
beam you will ask
thickness.
civil they will give you the about the beam. They will civil you can ask if
Because
they will tell you
generally
that
why I'm asking because based on this our input only they were going to decide the thickness and
strength number of members they are going to decide, but beam width is mostly standard, but how much members required that they will going to decide fully.
okay, sir. Thank you, sir. Right, sir. Thank you very much.
Okay. Okay, yeah. So beam width 2 meter. Okay, and then this so far clear. Conductor static tension
up to beam with clear, sir.
Yeah.
up to beam width clear. Okay,
With
now
Yeah.
next, since we are using the subconductors, so between the subconductors we are mentioning here my conductor to conductor spacing. What I mean by that again, I'm taking this example. So from one conductor to next conductor, this is 4 conductor per page. So one conductor to next conductor, the gap is 450 millimeter. This is a standard gap that we take. So 450 millimeter is my conductor to conductor spacing that we are mentioning here as an input. 450 millimeter means 0.45 meter. Again, this is a standard uh, this spacing distance between.
If any substation is one conductor is then what?
Note down the query. Now do not jump in the discussion. Not do not interrupt me. Otherwise, again I have to start from the scratch. In the last we have the Q&A. Then we can discuss again. Okay. You can tell me go to this page. I will go and then discuss with me. Okay, Rajdeep. Okay. So distance between subconductors and then distance between two adjacent spacers means because as you can see over here as well. Uh, we are providing the spacer and here you can say spacer span means every 2.5 meter we have to provide the spacer. This is for 220 kV, and when it comes to 400 kV, so every 6 meter 5 meter 5 meter means every 5 meter 4 meter. And when my short circuit current value increase, then spacer span decrease. So if you see 63 kiloampere, then every 4 meters, every 4 meter we have to provide the spacer. So that instead of 4 meter in my project I have used here 3 meter. If you want, you can use 4 meter as well. This is the standard that uh, uh, spacing that we take. So distance between two adjacent spaces 3 meter, right? So between two spacers, hope I am clear with what I mean by the 3 meter. Between two spacer means my foot 29 meter my length. So every 3 meter we have to provide, means between this much 10 number of spacers we have to provide. You can see here 9 number of spacer. So total number of spacer 9 numbers. Okay, and then spacer itself will have the weight. This spacer will have it. This is a spacer that we are providing every 3 meter. This spacer itself will have the weight. So along with this conductor weight, we have to consider the spacer weight as well. So here,
Sir, what is that material?
Rahul,
Aluminum.
there is a Q&A in the last. Come in the Q&A, okay. Do not
Okay.
jump during the discussion, please. Otherwise, I will not able what I need to deliver today. And then you have to come in the weekdays, okay?
Okay, sir. Okay. No.
Yeah. Same same material, aluminum that we are using for the conductor. Okay, let me SPACER. Might be we can get some spacers, okay? Spacers. Spacers shall be IS. The spacers are to be located at suitable spacing to limit the short circuit force as per 6065 by the wherever employer standard guarantees are being used. The spacer span different conductor span configure shall be as per XRD. The strung bus flexible types shall be used well. All coordinating spacer between shall be provided with active one spacer. Anyway, construction no management shall be used in except for GI, but shall be made to take care of fixing and moving during the so no magnetic metal shall be used in the fabrication of this spacer except for the GI bolts and nuts. So this is about the construction feature of the spacer. Test all those things. So you can refer this one. Now, back to the again calculation. Yeah. So number of spacer. Then here resultant spring constant of both support. The resultant spring constant of both support, it is 6 10 to the power 5. This value I am taking from the 60865. 60865, they have mentioned about this spring constant. Okay, based on the voltage wise they have mentioned. So this value I am taking from the 60865. Okay, I will tell you further that which formula which page, but this I am taking from the 60865. The resultant, you can see, I think there is one formula about the one statement. So I'm referring that statement. About this resultant spring constant. Anyway, I will take during the Excel about what the reference of this. Then weight of the spacer 2.5 kg weight that we can ask from the weight spacer supplier, and it is the standard weight that we take 2.5 kg. So this weight also you can consider. And the value of G everyone know 9.81. Distance between main conductors midpoint means R to Y and Y to B, that spacing. So this 7 meter, because the bay width was 27 meter, so that is why between R to Y, Y to B we have considered 7 meter, and between phase to gantry we have taken 6.5 meter. The 7 meter between R to Y 7 meter, and from Y to B again 7 meter. So phase to phase spacing. And lowest value of angle modulus become constant. This again I am taking from the 60865. I will tell you about this value in the Excel sheet. Okay, so here this spring constant 10 to the power 5. I think we have mentioned here 10 to the power 5 to 5, not 5 to the power 10 to the power 7, that you can see here. I am taking as okay, 5 10 to the power 7, 5 10 to the power 7. This reference I have pasted over here. You can refer here. Few constant value will be needed during the calculation. So this constant value I have mentioned here, 5 into 10 to the power 7, all coming from the 60865. So during the calculation I will take up this. And how to start the calculation, what is the approach? The calculation start with the 3 phase electromagnetic force calculation. So first of all, we calculate this force, the electromagnetic force calculations. Is it okay to start today? If all of you any problem, I can take in the next class. But for that, you need to available during the weekdays.
Yes, sir.
So you can take it in the next class. Too.
Next class is fine, sir.
Because I don't want that you just fed up with all those things and anything not clear, because this calculation take energy.
Yes, sir.
So it is involving a lot of calculations, so need some time.
Yeah. Okay. Okay. So
Sir, can you just share the PDF file of this calculator?
So we'll do class like we'll do class in weekdays, then we will discuss it. Okay, might be I will inform, but
The same way we did in the last week.
yeah, like that. Yeah, like that. Yeah. On Wednesday we have class, so like that. Yeah, but I will inform in the morning. Okay.
Okay, definitely no issue.
So please do share the calculation PDF file.
Yeah. Yes.
Sir, this 4,000 kg
Today,
that we have taken.
can you please hold on? Lalit, can you please hold on? What discussion was being held between you and Mr. Sohail? The two different approaches. If after the calculation sheet, how you proceed on the calculation. Once we understand that, if you could share the second path subsequent to the what progress of what is the flow of your session, it would be really helpful, sir, because that approach was slightly different. Everybody got into that flow, but thoda sa confusion bhi ho raha tha. It would be helpful, sir, if it is possible. What you understood today as a difference of design, if it is possible, sir.
Sir, actually what happened, I'll tell you two things we discussed today, sir, with respect to the approach. The first thing, that in my calculation I'm taking let me go back to this input parameters. So I'm taking this where is that conductor input? I'm taking 4000 kg directly over here. Okay, here sir, referring that this is a engineering practices that we take 1000 kg per conductor as a normal tension or a static tension. Okay, and for that I refer the power grid their erection manual. In that it was mentioned, so I was referring this document to support my assumption engineering practices. Whereas they told me that instead of taking as this reference in their company, what they do, they perform one sag and tension calculation first. Generally we do not perform, we perform it separately, but they are telling that instead of referring taking this reference, instead of taking this reference in their company, sag tension we also calculate, because this also required to civil team to know that how much tension stress coming on their structure. This also we need to perform, and we need to provide this along with the SCF calculation. So what happening in this calculation also, I'm assuming one static tension, which is again 1000 kg. You can see design tension per phase, so 2000 kg because twin conductor, so one per conductor 1000 kg we need to take, and so this is my design tension. Then I'm calculating here the final stress or final tension, which was coming the tension per conductor 929.79 kg, which is low, slightly less than the design tension or assumed initial tension. So instead of taking full 1000 kg per conductor, they will take 929.79 or 930 kg per conductor. So 930 multiplied by 4, right? So they consider this value here in the calculation instead of taking this one. This is one topic. This is one approach difference. Second thing, they in this side they are taking this formula, this FES formula for the reference purpose. FES formula on the page 28, and they are using this SCF formula. FES means SAG formula. SAG formula. This formula they are using, and in the calculations, and this SAG for and this SAG formula they are using in the SAG tension calculation Excel sheet. Whereas in my calculation, this SAG formula I have used in my SCF calculation. So they take the reference from the sag tension, but I am calculating here the sag BC I am calculating here. So I am not taking reference, I am calculating over here. Scales are
Right, sir. Right. Okay.
this was difference. So either you calculate here or you calculate in some another.
Can I add 2 more points?
Yeah,
the
sure.
Sir,
Welcome, dear. बताइए ना sir.
Generally, for the FST value, if we work on the Indian project, so we refer PGCL standard, which Raghav sir discuss. But in this value you have taken in the abroad projects or any renewable projects which we work in the India. So at that time, that is one challenge we face to overcome that comments, like how we can directly put 4,000 for the quad conductor in that case. So we have to perform first sec tension value, and according to the value of tension we put the value at that. So to understand from the client side, we can take reference for the sec tension.
Yeah, I get your point and what Raghav sir mentioned. Thank you, dear. Thank you for the input.
Okay.
Anything else, sir, if you want to add up for the better clarity to Khair.
Sir, actually, just for information, what is the sag value for this sag tension value for this calculation? Slightly below
sag value, sag is 0.768 meter. You can see BC is the sag.
Yes, 0.768, and that.
And tension we have considered the static tension FST that we have considered here. Okay, but if you want that, we will discuss anyway in other classes the sag tension. So here tension value coming here 29.79 kg, which we have taken 1000 kg. Okay, so
actually they are using this tension value.
Yeah, this tension value. Yes. They are not referring. They are not referring.
They are not supposing the 40.
Yeah,
as per the
not because as they have mentioned, because they have they like received comment that from where 4000 kg coming. Okay, so I refer the power grid. So instead of referring the power grid normal tension, they refer that this tension coming from the sag tension calculations. So instead of taking normal tension, they are taking
actually they are calculating actual value of the
actual
tension value. Tension value.
Yes, they are.
And based upon that, they are calculating the saturated force accordingly. The tower we are going to design.
Correct.
Cost optimization.
Yes. So they are going with the actual tension. And this is so for the tension they can submit this calculation that this is my reference for the tension calculation. Okay.
So what about the spaces, spacing between the spaces? Like, is there any calculation?
Say, do you perform any calculation for the spacers?
No, sir.
So how you
generally from the vendor document or OEM document, we can obtain the length.
Anyway, they're asking that span. Like I have taken 4 meter span, 6 meter span. You are asking about this, Ashwin?
Sir, actually, I have done one project in that. 1 second, I'll tell you. and that we have taken 2 meters. This was for 220 kV.
220 kV, yeah, 2 meter is fine because 2.5 kV, 2.5 meter we take, so 2 meter.
So it is directly, they just mentioned there was no background, nothing, just that's it.
Yeah, anyway. So anyways, this is the reference that you can take, Ashwin. This is the reference that generally most of the engineer will take 2 meter, 2.5 meter. So this is your reference for the space.
Yeah, actually, for a bidding that we have done, like they're given some screenshot from that. I've taken that spaces, number of spaces and all. But I was thinking from where they got this number. I just want to know that.
Might be this they have used. Might be.
Yeah, this is so much like this.
But we need to know that why we are using the spacers. The spacers are using to limit the short circuit force. Spacers are to be located at suitable spacing to limit the short circuit force as per 605 conductors are being used. The spacer spans for different conductors and configuration shall be as per the next 30. Okay, next 30 already we are writing. So this span we take, and then accordingly corresponding to that we calculate how much pinch force coming. Okay. Yeah, Lalit, tell me.
Yeah, this is for the flexible conductor, so we need calculation for rigid conductor.
Yeah, I was about to take it this as well. So now coming to the rigid conductor, this is this conductor. So what we do, Lalit, I'm telling as per the UK practices. So in the UK practice, we do not use the flexible conductor to make the main bus bar. We use the rigid tubular bus bar, and for that purpose, they do not calculate the short circuit means this calculation steps. They have a slightly different calculation approach, and their calculation approach is that they calculate the bus bar loading. So instead of telling the SCF calculations, their calculation is the bus bar loading calculation, means how much load considering the wind, considering the ice thickness, okay, considering the wind speed, and their wind speed also high like 30 meter per second. So consider the wind speed, ice thickness, conductor diameter, conductor type of the terminal connector, the flexible or the fixed. Okay, fixed are the simple connectors. So taking with the right hand side,
Simple and fixed.
yeah, fix on the right hand side might be fixed, on left hand side might be simple. So considering those inputs, they calculate how much loading of the bus bar coming on the equipment terminal head. So they check that whether their terminal head is properly is adequate or not adequate, plus how much the load coming on the equipment, and then how much load transferring to the structure. So slightly a different terminology and a little bit different way for the calculations. If time allow, I will take up that as well. Okay, Lalit, I will take up that as well. I'm aware about that calculations. I have completed that calculations for more than 8-9 project. Okay, but unfortunately, the Excel sheet I'm lagging. I'm not able to arrange the Excel sheet because I was performing that calculation for a company and I could not get the Excel sheet because I could not take the Excel sheet there. Excel sheet. But I'm developing the Excel, taking the formula, and in that same 60865 we refer. Okay, standard the same.
So for the load condition, like as per the National Grid Standard 3.1.4, so there are two load conditions for the one for the dead load, short circuit force, and there is a two type of force like horizontal and vertical force. So
Horizontal
there
and
are two
vertical force.
combination of load.
Yes.
Yeah. So as per the horizontal and vertical force, there are two different load combination we need to provide, and after that they will be considered how much load will be considered for this equipment like.
Yeah, yes, yes, yes. Angel, do you have any Excel, Angel? Because if you can share,
Yeah,
I can.
even just what happened, just I joined the now M group, and even I'm developing. I already developed by myself, so I can I'm not sure, but I can share, but I cannot say to give anyone, but I can share if anyone want to see how its load combination is there. Like
Yeah, okay, you can do that. That will be helpful.
I already develop by myself because they have lots of standard is there with the combination, because for the wind and ice load I need to uh, check with BS 1991 for the wind and 1993 for the ice load. So there is a two things we
Yeah,
need to
yeah.
consider
If you
for
can share, I
the.
can take up in that class because I have executed for many projects, so I have idea
Okay,
how
okay.
to perform the calculations. And,
Mm-hmm.
I have
Okay, okay. Yeah.
I was looking for a corporate company, so that corporate company have their own Excel sheet. So
Mm-hmm.
I'm using their Excel sheet and putting the value and calculating the load. But I could not take that
Mm-hmm. Okay,
data. So
no worry. I can share.
yeah,
Yeah, I can share like with the next class with my screen. I can share the screen and show how the load combination
perfect,
is there.
perfect. Yeah, yeah. If you can share the screen, I will make you host, and then you can explain that. Since you
Okay.
have recently
Yeah, yeah, yeah. No
developed,
worries,
so
no
you
worries.
can
Sure.
explain that
Okay.
as well, and I will add on my side
Okay,
as
okay, no.
well. Okay.
Yeah, even how to consider for the wind and ice load. So there is a two different standards they are using here for the
Good,
British standard.
good, Kenji. Good. Yeah, yeah, yeah. Thank you. So I will take your help for
Okay.
the tubular rigid bus bar. Okay, in the next class. Might be Lalit, that would be
Yeah,
helpful for you.
okay.
Okay.
Okay, okay, sure.
Sir, can
Yeah,
you
thank
refer
you.
to that PGCL sheet where the static tensions were mentioned at
I
4
will share Arnab in the
No,
portal.
sir, can you refer back? I have some question.
Say again.
That PGCL sheet that you were referring to, where the static tension of 4 ton was
I will
mentioned.
upload. You can check, then let me know. Okay, what the doubt you have. I will upload this.
No, there you told we have 100 kg per conductor per phase of tension, right? Okay, okay, I will check this. Yes, yes, I will check.
Yeah.
Sir, in slide number one, just go to one slide.
Slide one. Yeah.
Yeah, in the first wire and second wire, it is showing the current force, attraction and repulsion force.
Yeah.
It is the phase to phase or same phase subconductor it is
No, no,
showing?
face to face, face to face, face to face. For face to face, okay, but in the same phase, there would be maximum time the attraction forces, na? Because current flowing in the same direction.
Yeah,
In one phase,
yeah, right, right.
in any one phase, current flowing in the same direction. So in one phase, most of the time you will get the attraction forces. But in two different phases, like here are this UY. Okay. So
Mhm.
first wire, second wire, I mean here R phase and Y phase. Y phase and B phase. Like that you can assume.
Yeah.
Two different
In
phases.
that case, the repulsion forces will be applied.
Yes, 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 yes. Like as we have seen in this video. Two different, one phase
Yeah, yeah,
here,
right.
one phase here. Repulsion force. Okay.
Okay. And one thing, just if in the Excel sheet you are showing that flexible conductor calculation, no?
Yeah, yeah, flexible.
This is not
Yes,
for the
it's
rigid
flexible.
conductor.
Yeah, not for the rigid, the flexible conductor calculation. For the gantry and tower structure design.
For IPS tube, in the bus tube, whatever
IPS
you
tube
mentioned.
in the next class, Kanjal will going to explain. They will tell for the IPS tube. Okay.
Sir, can you go to slide number 13? Actually, there actually I got some. Can you please tell me the distance between the main conductor and main conductor midpoints? 7 meters.
The phase-to-phase spacing.
Sorry, sir?
Phase-to-phase spacing. R to Y, Y to B. Phase-to-phase spacing.
Oh.
From here to here, 7 meter. Or you can say from here to here, 7 meter. Okay. So in that project, 27 meter was my base span. Okay. So 27 meter we have divided, like from the center of this tower to first 6.5, then 7, then 7, then from here to center of this 6.5, like that divided. So 7 meter between phases.
This question may appear a bit silly, but these calculations are based on. I mean, this is really a gray area for me, and that is why I'm asking. The short circuit forces that we are referring to on the pulling, the supporting end at which the tension will happen. But the point is, is it independent of the phase on which the fault occurs, or it is meant to be a three-phase fault only?
Yeah, three-phase fault. Three-phase fault.
Acha. So,
yeah. If you see here in the calculations, I will take up the formula, sir. So if you see page 39, and in meanwhile, I will request you to go through this. You see here, I'm taking this one. Calculation.
Mostly we are taking like a three-phase fault.
Yeah, three-phase fault is.
Yeah.
Yeah, yes.
Okay, thank you.
Yeah. So here I'm taking the three-phase fault. Okay. Electromagnetic force.
And the 608, even if you go with the same thing, there is in the 60865 they provide like three-phase fault, line to line fault, and line to ground fault. But as per the like client requirement and in every like common manner, we are doing the only three-phase fault.
Yeah, because we need to take that one fault occur between three phases, then how much force coming? Obviously, so we have to go with the three-phase
Yeah,
fault.
correct.
No, sir, the premise of my question was whether for a three-phase fault, the equivalent force acting on the center of the supports, that is for all three, it is equivalent to one force acting on the Y phase. Now, supposing RYB is there, then all of this force, three phase shorting together, would be acting in a single direction on the Y phase, isn't it? That is what I'm trying to understand. And that is how it is coming out, because forces would not be equivalent on all phases at the same time. That is what is my apprehension.
Okay, sir.
Am I right or am I wrong?
No, you are correct. You are correct. You are going very like deeper way, but yeah, in that way you are correct. You are fine, sir.
Will this be discussed or it is meant for general understanding?
General understanding. We take three phase short circuit current, and considering three phase short circuit current, when any three phase fault occurred, how much force coming, that force we are calculating. Okay, so per phase, and like what I can say.
Sorry to interrupt you. Like, but if you are considering this threefold, okay, three-phase fault, line to line force, and line to ground force. So if you are calculating this three force, so highest force is three-phase fault. So that's why they are considered this one.
No, I understood the point. That is well taken. It is there from our academic days. The point of force, I mean, is it R phase, is it Y phase, or is it B phase?
So, sir, not on the point of force. Like this is the force. How much coming on the structure means like take three phases, and then all three phases sort together, sir, and then here one gantry and here one gantry. So I'm considering three phase sort together. Then how much force coming on the gantries that we are calculating. Okay, I'm not telling this is on the R phase, on the Y phase, on the B phase. Point I'm telling.
I get your point.
Yes,
I
sir.
get the point. Thank you, sir. Thank you. I'll discuss with you in person. Thank you.
No, no, sir. You are correct in a very deeper way. You are correct that at what point,
I
what
think
center
what
of this
he's
force.
asking is the whatever the force and the tension is coming as it is connected on a common beam. So it is kind of distributed force that is completely will be
Yeah,
distributed across the
like that.
cavity and
Yeah,
the spar.
like that. We can also say distributed
Yes, yes, yes. So it's not like point force or something like
point force. Yeah. So the distributed. Okay, but anyway, that's fine, sir. That's fine. That we consider that when it happened, then how much force. Okay, anything else? Like I think we spent 2 hours just to discuss the basic background about this calculus. Anyway, that's fine because when we'll go the calculations, this basic discussion will help us. Anything else?
Sir,
Yeah.
Sir, suppose in only one conductor is using, then the spacing would be zero. Yeah. When you are
Yeah. Then
using
no need to
four,
take. Then that value will be zero. In Excel, put the value 0.
yeah, because here we are taking 450
Yeah. So that would be
millimeter.
everything would be 0. So like go in the same here. Here I will go, and then what I will do if I am using single conductor. So first of all, this between two adjacent spacer here I put 0. Okay, number of spacer 0. No any spacer. This would be there. S would be there, but weight of spacer 0. So all those things would be 0.
Would be zero.
Yes.
Yeah.
For maybe this will
sir,
come for 132 kV.
Okay. Yeah, right. Right.
my question is that the pinch force is applicable for the subconductor. So is it happening due to the short circuit force, or it is a individual force happening between the subconductors?
Which page? 4.
Pinch force, pinch force.
Pinch force, yes, due to the subconductor only. If there is no subconductor, so this force no need to calculate. Due to the
Means
subconductor.
due to the subconductor means if there is a short circuit, will it put any effect on the pinch force or not?
Yeah. If there is short circuit and there is like subconductors or bundle conductors, so the bundle conductor will again they will attract. Like you can see here, I have put here subconductors. Due to the
Yes.
short circuit, it is conductors are clashing. So in order to avoid that clashing, we have provided the spacers. Okay, and then conductors resulting the pinch force. Now you see they are resulting the pinch force attract, and then it is like this position. Okay, so
Okay. But that means it is happening due to the short circuit force.
yes, short circuit.
Okay.
Okay,
Okay, sir. Thank you.
okay. Thanks.
Raghav, could you go please this input slide like 10 number?
Yeah.
Not this one. In the some case, like you mentioned, like height of the conductor is both like low height and high height. It's about a 22 meter. I'm not sure where is it. Like, can you go in the calculations you mentioned? I'm not sure.
No worries. So we have discussed.
No.
Angel, let me go one by one. So this page, then we discuss this page, and then here, then standard, and then what is the meaning in layman language about these forces, and then three force and formula we will take from 60865. So we discussed
Yeah.
inputs. Then we took one example, one extract from the layout drawing. For that we are performing the calculation, and then here we discuss the system input parameter like my voltage, current, short circuit current, and then we discuss my conductor input parameters. So this we discuss, and then we discuss since ACs are 650 I'm taking, but usually we take Panther, Jabra, those conductors. So for that, I have make one table for the ready reference so that anyone doing so they can refer this one. And then we use the alpha Greek alphabet, so this symbols and then conductor span. So we discuss till here the conductor span.
Not here. I think. Can you go on the calculation?
Calculation, yeah, I can go, but I have not started so far the calculation. Yeah.
No. I'm just asking about the input.
Yeah, input, yeah, here. So system
You
volt is 500
mentioned.
kV. So let us see. The system volt is 500 kV, high
No,
system.
it's. Mm-hmm.
Yeah. So like short circuit current and conductor detail, then conductor number of
No,
subconductor.
I'm asking about the height of the, like, it's, you mentioned like 22 meter
No, that
somewhere.
height, I think you were asking about that actual conductor span that we calculated 29 meter.
No. It's a height, like how much above, like, I'm not sure where I can see. I forgot. Okay, let's
Height
leave
is
it.
height is not.
If I have.
Yeah, okay. Have a look.
Yeah, it's not a height. Right?
No, but you can have.
I'll check if
Okay,
I.
yeah. Let me know in the
Yeah.
next class.
Okay, sure. Thank you.
Thank you for your attendance. Thank you for your time. Okay, let's connect in the next class for the SCF calculations. Okay.
Thank you, sir.
Thank you.
Okay.
Thank you, sir.